Welcome back, dear students. Another good short numerical from engineering mechanics. You are likely to get such type of problems in GATE examination because the time duration it requires to solve the problem will be around 1.5 or 2 minutes at the most. So expect this kind of questions. Problem set 2.4, solution to 2.59. Determine the axial force induced in each bar of the system shown in figure P. This is figure P, due to the action of the applied forces P. If you look at AC is a bar, AD is a bar, CD is a bar, CB is another bar. So there are 1, 2, 3, 4, 5 bars. They are connected as shown. At this point there is a force P to this side, to the left. At this point there is a force P towards the right. Now, so far we have been discussing method of projections. In problem set 2.4 of engineering mechanics by Professor Timoshenko, we are following method of projections and applying sigma x and sigma y equal to 0 to find the different values of the axial forces. Right. So before I proceed, let me repeat this thing which I had earlier explained in previous videos. Suppose from O to C represents a force F making angle theta with the horizontal. So this is your x-axis, suppose, and this is your y-axis. This is the origin. So from the tip of the vector, if you drop a perpendicular on x-axis, this becomes 90. If you drop a perpendicular on y-axis, this becomes 90. And in this triangle, in triangle OAC, right angled at A, if you take cosine of theta, that will be base over hypotenuse, and if you cross multiply this one, OA, you get as F cos theta. And similarly, if you take sine of this angle in the triangle OAC and cross multiply, you get AC as F sin theta. And since AC is equal to OB and AC is also pointing in the same direction, therefore OB, which is F sin theta, is the y component of the force F. Means instead of considering this force F, you can consider the combined effect of F cos theta and F sin theta. But in certain situations, as we discussed in previous problems, you come across a force like this. So what you have to do is you translate this force to this side. Okay. So this theta becomes equal to theta here, which is convenient to take the angle theta at the origin of the vector. Then you can apply like this. This becomes F cos theta, this becomes F sin theta. So the same thing I have redrawn here. This force F making angle theta with the x-axis is translated from this point to this point, keeping the length same, means the magnitude of the force remains same, and keeping the angle same. So this part becomes your F cos theta and F sin theta. Here you can do the same thing, but you have to be very careful. Since this is your F, since this angle is theta, then this angle is also theta. So this is your F of cos theta, and this is your F of sin theta. And this F of sin theta is along y-axis, so you can shift it from here to here, because in vector analysis we know as long as you don't change the length of the vector, means you are not changing the magnitude, and as long as you are not changing the direction, this direction is same thing as the y direction, a vector can be shifted anywhere in space. Given a vector like this, having some magnitude and direction, you can shift it parallel to itself. You can shift it to this side, keeping the length same and the direction same. You can shift it to this side, keeping the length same and the direction same. You can shift it here also, keeping the length same and the direction same. So now since we are applying the method of projections, we need to have an angle like this or like this, so that we can split the given vector into rectangular components, one along x-axis and the other along y-axis. Then apply sigma x is equal to 0 and sigma y is equal to 0. And here in the given problem, since the angle is not given, let this angle is equal to alpha, and this angle is equal to CAD. CAD is equal to alpha, CDA. CDA is equal to beta, and angle CBD is equal to, suppose, gamma. So that is what I am saying. So we need an angle to split a vector to components along x-axis and y-axis. Therefore I have assumed angle CAD is equal to alpha, and angle CDA is equal to beta, and angle CBD is equal to gamma in the given diagram. Now if you look at the given diagram, there are 4 concurrent points: point A, point B, point C, point D. But if you look at carefully, there are less number of unknown forces at A and B. If you consider point A and B, the number of forces, unknown forces, are less as compared to C and D. So it will be wise to apply, draw the free body diagram either at A or at B, then resolve the forces, different forces, into rectangular components, and then apply sigma x is equal to 0 and sigma y is equal to 0. Now, to brief you again, this point is pulled with a force P, the point B. This point is pulled with a force P. So, these bars are pin jointed at A, C, D and B. So the bar AC will be under expansion, the bar AD will be under expansion, the bar CB will be under expansion. So let us consider the point A. Since AC will be under expansion, so the tensile force will be let it be S3. To this side is P, and your S1 in the bar from A to D is bar 1, so let it be S1. So at point A there are 3 forces, P, S3 and S1. This angle is alpha. So P and S1 both are along x-axis, so we need to only split the S3 into rectangular components. So I have drawn the free body diagram for you at A. Once that is understood, then it is very simple. So this is the free body diagram at A. At A, this angle is alpha. That is same thing as this angle. This is your point A. So to this side is S1, to this side is P, to this side is S3. So now this S1 and P, they are already along x-axis, completely along x-axis. So neither S1 nor P will have any y component. So only S3 will have a y component, x component. If you drop a perpendicular from here, this angle becomes 90. And if you drop a perpendicular from here, this angle becomes 90. This is the vector S3. So this is your x component of S3, which will be from here to here. This will be your S3 cos alpha, and this one, that is same thing as this one, will be S3 sin alpha. S3 sine alpha, this one from here to here. So let us apply sigma y is equal to 0. Why I am applying sigma y is equal to 0? Because there is only one force along y axis. So it will be easy to find S3 quickly first. So there is no force to this side to balance it. And sigma y has to be 0. Therefore S3 sine alpha has to be 0. So S3 sine alpha is 0, sine alpha is multiplied, goes to the other side, 0 over sine alpha, 0 over something is 0, so S3 is equal to 0. Now, then let us apply sigma x is equal to 0. If you look at the component of S3 along x-axis, that is from this point to this point, is equal to your S3 cos alpha, and S1 is in the same direction, so both will be added. So S1 plus S3 cos alpha will be equal and opposite to P, so that sigma x will be 0. So by putting sigma x is equal to 0, P is equal to S1 plus S3 cos alpha. Now, since S3 we found out to be 0, 0 into cos alpha is 0, so we are left with S1, so P is equal to S1, that is a tensile force. So S1 is equal to P, that is the tensile force. Now let us do the free body diagram at point D. Let us do the free body diagram at point D. You can apply the free body diagram at point B, which will apply later on. So let us begin with D. Now this is your point D, that is same thing as this point. Now for the point D, S1 will be to this side, same S1. That is what I have shown here. And this is the bar 4, so let it be S4, the axial force will be away from the point D. S4, the axial force away from the point D. And if you look at the bar from D to B, that is bar number 2, that is S2 to this side. So there are three forces, S1, S2 and S4. At point D, S1, S2 and S4, this is making angle beta, which I have considered it as beta. So if you drop a perpendicular from here and one on here, this much will be your S4 cos beta and this much will be your S4 sin beta. Along y-axis, there is no force to this side. Sigma y has to be 0. Therefore, this whole thing, S4 sin beta is equal to 0. Now therefore, S4 is equal to 0 over sin beta, 0 over something is equal to 0. So, S4 is 0. So, S1 is calculated, S3 is calculated, S4 is calculated. Let us apply sigma x is equal to 0. This S1 is along negative x-axis, and this component from here to here, that is S4 cos beta, is also along the negative x-axis, so both of them will be added, means S1 plus S4 cos beta, they are in the same direction, that is, and the sum of these two is being opposed by S2, so sigma x is equal to 0. Now implies now since S4 is equal to 0, put 0 here, 0 into cos beta is 0, so we are left with S1, S1 is equal to S2. And since S1 was equal to P, therefore S2 is also equal to P, so S1 is also the tensile force. Now finally let us apply free body diagram at point B. Free body diagram at point B, that is this point, P is to this side. This is your S5, and for the point B, this S2 will be towards the left. So that is what it is shown here. P, S5, S2, this angle is gamma. So if you drop a perpendicular here, this much will be your S5 sin gamma. There is no force to this side. This is y-axis. Some sigma y is equal to 0. Therefore, S5 sin gamma is equal to 0. So So if you take sine gamma to this side, 0 divided by sine gamma is 0. So S5 is equal to 0. So S5 is also 0. There is no need to apply sigma x to find S2 because S2 is already found out. But still, if you are interested, you can apply sigma x. Now here, S1 is to the left hand side, that is along negative x-axis, and this component from here to here, that is equal to S4 cos beta, is in the same direction as S1. So S1 plus S4 cos beta will be equal to S2. So S2 plus S5 cos beta, sorry, S2, I missed something, sigma x, S1 plus S4 cos beta, sorry, not beta, cos gamma, this angle is cos gamma, S4. This is S4, let me check, sorry, this is not S4, this is S5. This is S5. If you look at the diagram at point D, this is your S5. So, not S4, this is S5. So S5 is found out to be 0. Make a slight change here. This is S5, not S4. So this is your S5 cos beta, and this is your S1. Both are in the same direction. So S5 cos beta plus S1 is equal to S2. Is equal to, so S1 plus S5 cos beta is equal to S2. So S2, oh sorry, I am looking at a different point. Sorry, I was explaining this, not this. This is all right up to this. This is S4. This is S4. This is S4 sine beta. I'm sorry, this is also S4 cos beta. I was supposed to look at this diagram. Sorry for the mistake. So here, this is S4. This is S4. This is S4 sine beta. This is S4 cos beta, and this is S1. This part is over. Let us come back here. This is S5 at point B. Point B. This is S2. This is S5. So this is S5 sine beta, and the component of this towards this will be your S5 cos gamma. This will be S5 sine gamma. So if you apply sigma y is equal to 0, S5 sine gamma will be 0. Sine gamma goes to this side. So 0 over something is 0. So S5 is 0. There is no need to take your sigma x is equal to 0. But still you are interested. S2 plus from here to here S5 S5 cos gamma will be equal to P. So S2 plus S5 cos gamma is P. Since S5 we just calculated as a 0, the 0 into this thing is 0, so S2 is equal to P. That is also, since it is already calculated, there is no need to put sigma x is equal to 0 because S2 is already calculated. I am sorry. This, let me draw the diagram here again, explain you. This was at point D, so this was your S4. This was your S4. And this was your S2. And this was your S1. This angle was beta at point D. Let me repeat because things went wrong here. While explaining, I was supposed to explain with this diagram, but I shifted here. So here the component of S4 along y-axis will be S4 sine beta. that is what equal to 0. So sine beta goes to this side, is divided, so S4 becomes 0, and sigma x, that is from here to here, is equal to your S4 cos beta, this one and S1 both are in the same direction, that is being opposed by S2, so S1 plus S4 cos beta. So S1 plus S4 cos beta is equal to S2. Now since S4 is 0, 0 into this thing is 0, so S1 is equal to S2, and since S1 was equal to P, so your S2 is also equal to P, so S1 is also P, and the force is tensile. Something went wrong here while explaining this sigma x is equal to 0. I considered this diagram, which was wrong. I was supposed to consider. So just remember this. Just forget about this overwritings, and things are clear here.